Hello and welcome back to Intro to AI course. So we ended the last video on the uninformed search category among the search strategies. We studied about the breadth first search, and in this video we are going to be taking a look at depth first uninformed search. So after breadth first search, what is depth first search algorithm? Depth first search always expands the deepest node possible for each node that encounters first. It uses the LIFO queue. A LIFO queue means that the most recently generated node is chosen for expansion. This must be the deepest unexpanded node because it is one deeper than its parent, which was the deepest unexpanded node when it was selected. But this is again not the complete solution, as it may get stuck indefinitely because of deep branches and restricted state spaces, as we will see later on. So let's take a look at an example. We will use a similar example like the last video. As you can see on the right, we have the image of the path we have to traverse, and remember that in our case the goal state is going to be the G node. Starting off our queue with just the initial state S. So the idea here is that moving from the initial state S, we start with the first child node of S, which is A, and then traverse each node of A until we cannot go any deeper. And this is the depth first search algorithm via search trees. So starting from S, the first ones are A and B. So we write those, and now we have the pathways of SA and SB. And then starting from the first node A, we explore it to as much depth as we can go. So the possible states from A were B and D, and now the first node B, and let's explore that to the maximum depth as much as we can. So the possible nodes from B was only one, which was C, and from C we can go even further to E, and from E we cannot really go anywhere else. So we have reached the maximum depth. Now in our queue, the entry that was most recently added was the SABC pathway from start to the E state. All the others could be disregarded and there would be no need to calculate those paths. But the problem is we have not yet completed the solution. We have not reached the goal state. And of course the goal state is the G node. So we are yet to reach that point of the algorithm. And well, to achieve that, what we can do is we can backtrack. A variant of depth first search is called backtracking search, which uses still less memory. In backtracking, only one successor is generated at a time rather than all successors. Each partially expanded node remembers which successor to generate next. In this way, memory is saved, and if somehow the same node is encountered which was calculated before, the calculation already stored would be used, and this saves the memory. So moving on, just like how we did the last time, this time after coming back to node A, we can now focus on the other node of A, which is D, and expanding D results in the node G, which is the goal state. And so with that, we have searched the solution and were able to locate and find a path to the goal state node. This is slightly better than the breadth first search because of going depth first for each node starting from the first one. But it is still inefficient. And the reason for that is that it is only good if the goal state node is among the first nodes of the initial state or nodes. And if the goal state was at the last node, it would take a lot of calculations and time to calculate, rendering this search strategy inefficient. But we do have something called the depth limited search. Depth limited search is a variation of depth first search strategy that uses a predetermined depth limit L. That means the node at depth L are treated as if they have no successors. This approach is called depth limited search. The depth limit in this scenario involves the infinite path problem, because even if there are infinite or trillion depth of a given node, the search algorithm will stop and won't go any further into depth. This could save us from massive memory in use if the goal state isn't in the node being calculated. But unfortunately, this method also introduces to incompleteness of its own. By having the limit on the depth, if the goal state node has the depth larger than the set value of maximum depth, we will never reach the goal. So that is also a problem. So how can you solve such a problem? We are already rapidly progressing towards clever ideas for agent to solve weird problems. So why not you give it a try and come up with a solution, and we can see what we can do in the next video. So this has been a little bit about the uninformed search strategies, and we are going to soon look at informed search strategies. And of course, with that being said, see you in the next one.